Imagine looking up at the night sky, marveling at the vastness of our solar system, planets orbiting the sun in perfect harmony. Now what if I told you that a similar system of motion exists right inside the atoms that make up everything around us? It may sound unbelievable, but the structure of an atom, with electrons revolving around a nucleus, bears a striking resemblance to the solar system. At first glance, atoms and solar systems couldn't be more different. One is the fundamental building block of all matter, while the other is a massive cosmic entity. But when you break down their structures, we can start to see surprising similarities. Just like how planets orbit the sun under the force of gravity, electrons revolve around a nucleus due to electromagnetic forces. This parallel can help us understand the fundamental laws that govern the smallest particles in the universe, as well as the largest celestial bodies. However, this comparison goes beyond just appearances. What if the motion of electrons in an atom is more than just an orbit? And what if the movements of planets are influenced by more than just gravity? Today we'll explore the deeper connection between the atomic world and the cosmos, and question whether the universe follows similar patterns, from the quantum scale to the galactic scale. Join me as we dive into this fascinating analogy and uncover how these two seemingly unrelated systems might actually reveal the same underlying principles of the universe.
Before we dive into the comparison between atoms and the solar system, let's first understand how an atom is structured. Every atom is made up of a dense central core called the nucleus, which contains protons and neutrons. Orbiting around this nucleus are much smaller particles called electrons. The nucleus is incredibly small compared to the overall size of the atom, but it holds almost all of the atom's mass. The protons inside the nucleus have a positive charge, while neutrons have no charge at all. Together, they form the heart of the atom, much like the sun forms the heart of the solar system. Surrounding the nucleus, we have electrons, negatively charged particles that move rapidly in what appear to be circular or elliptical orbits. These electrons are attracted to the positive charge of the nucleus, much like planets are pulled towards the sun by gravity. But there's more to this story. While early models of the atom, like the Bohr model, depicted electrons as tiny planets orbiting the nucleus in fixed paths, quantum mechanics tells us something different. Instead of well-defined orbits, electrons exist in a cloud of probabilities. This means we can't know their exact location at any given moment. We can only estimate where they might be. On the left, you see the classical Bohr model, which represents electrons as distinct particles in fixed orbits, similar to planets around the sun. On the right, we have the quantum model, where electrons behave more like a fuzzy cloud of energy existing in many places at once. Even though electrons don't move in the same predictable way that planets do, the idea of attraction to a central core remains the same. In the solar system, planets are held in orbit by the gravitational pull of the sun. In atoms, it's the electromagnetic force between the negatively charged electrons and the positively charged nucleus that keeps electrons in motion. So, in summary, the atom consists of a dense nucleus at its core and fast-moving electrons surrounding it, held together by the attractive force between the positive charge of the nucleus and the negative charge of the electrons. This is where the analogy between atomic structures and the solar system starts to take shape. Now that we have a better understanding of atomic structure, let's take a step back and see how the solar system mirrors this same pattern on a cosmic scale.
Now that we've explored the structure of an atom, let's zoom out, way out, and shift our focus to something much larger, our solar system. At first glance, it seems like the opposite of an atom in terms of scale, but when we look closely, the solar system shares striking similarities with atomic structures. At the heart of the solar system lies the sun, a massive, glowing ball of gas that exerts an immense gravitational pull. The sun is so massive that it holds every planet, moon, and asteroid in orbit around it. This is similar to how the nucleus of an atom with its positive charge attracts and holds electrons in place. Just as electrons revolve around the nucleus in an atom, the planets orbit the sun. The closer a planet is to the sun, the faster it moves in its orbit. For example, Mercury, the closest planet, completes a full orbit in just 88 days, while Neptune, much farther away, takes a whopping 165 years to orbit the sun. This variation in speed is another parallel we can draw with electrons, where those closer to the nucleus have higher energy levels. Now let's imagine shrinking the entire solar system down to the size of an atom. If the sun were the nucleus and the planets were like electrons, this system would resemble the atomic model we discussed earlier, just at a much larger scale. But what keeps these systems together? In the solar system, the sun's gravitational pull is the force that binds everything, much like how the electromagnetic force binds electrons to the nucleus in an atom. While the forces are different, the principle is similar. A powerful central force holds the smaller bodies in orbit. When we look at the bigger picture, the solar system is just one of many systems in the universe, much like an atom is just one of many that make up matter. In fact, there are billions of solar systems in the Milky Way alone, and each one follows the same pattern of having a central star and orbiting bodies, just as every atom has a nucleus and surrounding electrons. While the analogy between atomic structure and the solar system helps us understand these systems visually, the motion of electrons is more complex than that of planets. Planets move in well-defined orbits, but electrons exist in a state of probability. They move so fast and unpredictably that they behave more like a cloud of energy around the nucleus rather than following precise orbits. So, while the solar system and an atom share structural similarities, the scale difference is staggering. Atoms are so small that we measure them in nanometers, billionths of a meter, while the solar system spans billions of kilometers. But despite these differences, both systems show us how smaller objects orbit around a central mass, guided by powerful forces. Whether it's the tiny invisible atoms that make up everything in our world, or the vast solar systems spread across the universe, the same principles of attraction and orbit are at play. Both are examples of how nature organizes matter, from the smallest scales to the largest. But what if these orbits, whether of electrons or planets, are an illusion? In the next segment, we'll dive deeper into the quantum world and explore how the movement of electrons and planets might be more complex than we ever imagined.
So far, we've discussed the striking similarities between atomic structures and solar systems, where electrons seem to orbit a nucleus in much the same way that planets orbit the sun. But what if I told you that these orbits are, in many ways, an illusion? To understand this, we need to dig deeper into the strange world of quantum mechanics and relativistic physics. In the classical model of the atom, electrons are depicted as tiny particles moving in neat, circular paths around the nucleus, similar to how planets move in well-defined orbits around the sun. This idea worked well for early physicists, but it wasn't long before quantum mechanics revealed a much stranger reality. This is where the Heisenberg uncertainty principle comes in. It states that the more precisely we try to measure the position of an electron, the less precisely we can know its momentum, and vice versa. This means that the classical idea of electrons following an exact path around the nucleus breaks down at the quantum level. In the quantum world, particles like electrons don't behave in the predictable, orderly way that planets do. While planets have a clear, defined orbit, electrons behave more like waves of energy that are spread out across space. The idea of a fixed orbit is more of a useful approximation than an actual description of reality. But what about the solar system? Is the orbit of planets around the sun also an illusion? In a sense, yes. According to Einstein's theory of general relativity, the planets aren't really orbiting the sun in the way we might imagine. Instead, they are following curved paths through space-time, which is warped by the sun's massive gravitational pull. In Einstein's view, space and time are like a fabric, and massive objects like the sun bend this fabric. Planets move along the curves created by this bending, so their orbits aren't due to a mysterious force pulling them in a circular path. Instead, they are simply following the natural curves of space-time created by the sun's gravity. While planets in the solar system still move in a somewhat predictable, measurable way, their motion is influenced by the curvature of space-time. At the atomic level, however, the motion of electrons is even stranger, governed by quantum probabilities rather than fixed paths. These two realms, quantum mechanics and general relativity, describe very different worlds, but both challenge our classical understanding of orbits as simple circular paths. So, are orbits, whether of electrons or planets, real, or are they just a convenient way for us to describe the complex interactions that govern these systems? While we often visualize these orbits as simple and neat, both quantum mechanics and relativity show us that reality is far more complex. In both the atomic and cosmic realms, what we perceive as orbits is more of an illusion created by the forces at play, whether it's the probabilities of quantum mechanics or the curvature of space-time. Both systems remind us that the universe operates in ways that often defy our everyday experience and intuition. In the end, whether we're talking about electrons or planets, these orbits are just one way to describe the incredible complexity of the universe. But this comparison between atomic structures and solar systems reveals deeper truths about how everything in the universe is interconnected. In our next segment, we'll explore what this analogy means for our understanding of the universe as a whole.
Now that we've explored both atomic and solar system structures and delved into the illusionary nature of orbits, the question arises, why does this analogy between atoms and the solar system matter? Beyond the visual similarities, could this comparison unlock deeper truths about the nature of the universe and our understanding of science? This analogy between atomic and cosmic systems reminds us of an intriguing possibility, that the universe may follow similar patterns and structures on vastly different scales. Atoms make up everything around us, including the stars and planets in our solar system. In turn, solar systems are part of galaxies, and galaxies form the larger cosmic web. The structures of nature, from the smallest particles to the largest celestial bodies, are interconnected, suggesting that similar rules may govern both the micro and macro scales. One of the most significant implications of this analogy is that it challenges us to look for a unified understanding of physics. Right now, quantum mechanics governs the behavior of subatomic particles, while relativity explains how massive objects like planets and stars move through space-time. These two realms seem disconnected, but what if the analogy between atomic and solar systems is a clue that there could be a unified set of laws governing both? For decades, physicists have been searching for what is known as a theory of everything, a set of laws that can explain both the quantum and relativistic worlds. Could the analogy between atoms and solar systems be a sign that such a theory exists? If we can find the common ground between the behavior of subatomic particles and the motion of celestial bodies, we might finally unlock a deeper understanding of the universe's fundamental forces. This analogy also points to a concept seen in nature: self-similarity, where patterns repeat themselves across different scales. We see this in fractals, where a pattern repeats infinitely, from the smallest scale to the largest. In a similar way, atomic structures and solar systems share this self-similar pattern. Both are organized systems held together by forces of attraction and interaction. From atoms to galaxies, nature seems to organize itself in repeating patterns. Interestingly, the analogy between atoms and the solar system isn't just a modern scientific observation. It taps into ancient philosophical ideas about the microcosm and the macrocosm. For centuries, scholars and philosophers have believed that the small-scale structures of reality, whether atoms, cells, or even human beings, mirror the larger universe. This idea that the universe is a reflection of its smallest parts has deep roots in human thought. And this brings us to a profound realization. We, too, are part of this cosmic structure. The atoms in our bodies were formed in stars billions of years ago, and the same forces that hold atoms together are responsible for shaping solar systems. In a very real sense, we are connected to the universe at every level, from the atomic scale to the cosmic scale. By understanding the connection between atoms and the solar system, we not only deepen our understanding of science, but we also gain a broader perspective on our place in the universe. We are small, yet we are made of the same cosmic material that fills the universe. This analogy reminds us that the mysteries of the cosmos can be found within each atom and within each of us. As we continue to explore this analogy, new questions emerge. What other patterns might we discover in the connection between the atomic and cosmic worlds? Could this analogy reveal deeper secrets about the origins of the universe? And what technological breakthroughs might arise from understanding these hidden connections? The answers to these questions could change the future of science and human exploration. The analogy between the atom and the solar system invites us to rethink our understanding of the universe from the smallest scales to the largest. It challenges us to search for deeper connections between quantum mechanics and relativity, and between ourselves and the cosmos. As we continue to explore these ideas, we may uncover profound truths that reshape our view of the universe and our place within it. Join us next time as we dive deeper into these connections and explore what the future holds for our understanding of the universe and the forces that shape it. From atoms to galaxies, we're only just beginning to uncover the hidden links that connect us to the star.
While the analogy between atomic structure and the solar system is captivating, it's important to recognize that this comparison is not without its limitations. As much as the two systems may appear similar at first glance, there are significant differences that emerge when we take a closer look. In this segment, we'll explore the key criticisms and challenges that come with this analogy. One of the first major criticisms of this analogy is rooted in quantum mechanics. Unlike planets in a solar system, which follow predictable orbits, electrons do not follow simple paths around the nucleus. In fact, the classical image of electrons orbiting the nucleus like planets is outdated. According to quantum theory, electrons exist as probability clouds, meaning their exact position at any given moment is uncertain. They don't behave like solid objects, but rather as waves or particles depending on how we observe them. Electrons also don't exist in simple circular or elliptical orbits. Instead, they occupy regions called orbitals, which have complex shapes and can extend far beyond what we would expect from a solar system model. These orbitals describe the likelihood of finding an electron in a certain region around the nucleus, but they don't follow a fixed path like planets around the sun. Another key limitation is the nature of the forces at play. In a solar system, planets are bound to their star by gravity, a force that governs large, massive objects. In an atom, electrons are bound to the nucleus by the electromagnetic force, which is much stronger but operates at a far smaller scale. The distinction between these two forces is crucial because it affects how objects behave. Gravity is a relatively weak force compared to electromagnetism, but it acts over long distances, whereas electromagnetic interactions dominate at atomic scales. The difference in size between an atom and a solar system is immense. If we were to compare the two systems directly, it becomes clear that their scales are completely different. Atoms are tiny, measuring only a few angstroms across, while solar systems span billions of kilometers. Additionally, the energy levels involved in atomic interactions are on a completely different scale compared to the energy required for planetary motions. This makes the analogy more symbolic than literal. The analogy also falls short when we consider the laws that govern these systems. While planetary motion can be explained using classical mechanics, Newton's laws of motion and universal gravitation, atomic systems are governed by quantum mechanics. At atomic scales, classical laws break down and new principles take over, such as the uncertainty principle and wave-particle duality. These concepts don't have equivalents in the world of planets and stars, meaning the analogy between the two systems can only go so far. Finally, atomic structures are far more complex than solar systems. Atoms aren't just composed of electrons and a nucleus. The nucleus itself is made up of protons and neutrons, which in turn are composed of quarks. These subatomic particles interact via the strong and weak nuclear forces that have no analog in the solar system. This added complexity in atomic systems means that the simple solar system model doesn't capture the full picture. In summary, while the atomic solar system analogy is useful as a teaching tool and a way to visualize certain aspects of atomic structure, it can also be misleading. Simplifying atomic behavior to resemble planetary orbits can obscure the true complexity and nuances of quantum mechanics, leading to misconceptions. It's important to understand the limitations of this comparison and approach it with caution. By understanding these criticisms, we can better appreciate both the power and the limitations of the analogy. It's a helpful metaphor, but it's not a perfect representation of reality. Recognizing where the analogy breaks down allows us to gain a more accurate understanding of both atomic and cosmic systems, and it invites us to explore new ways of thinking about the universe. As we continue to advance in both quantum mechanics and astrophysics, we may find new analogies or models that better explain the true nature of reality. The atomic and solar system analogy, though imperfect, is part of a long tradition of using metaphors to explore complex ideas. As science progresses, so too does our ability to describe the universe with greater accuracy and understanding. What do you think? Can we fully compare atoms to the solar system, or is the analogy too simple? As we've seen, the analogy between atoms and the solar system can be a helpful tool, but it also has its limitations. What's your take? Do you think this analogy still holds value in modern science? Or should we explore new ways to visualize atomic structures? We'd love to hear your thoughts in the comments below. If you enjoyed this exploration into the intersection of atomic physics and astrophysics, don't forget to give this video a thumbs up. And if you're eager to dive deeper into the world of science, make sure to subscribe to our channel and hit the notification bell so you don't miss any of our future videos. In our next video, we'll be taking a closer look at quantum mechanics, diving into the strange and mind-bending principles that define the atomic world. You won't want to miss it. Thank you for joining us on this journey through the cosmos and the atomic world. Science is filled with analogies and models, each one offering us a glimpse into the intricate designs of nature. But it's also important to challenge these ideas and push beyond the surface. It's in that spirit of curiosity and exploration that we continue to uncover the mysteries of the universe, both large and small. Stay curious, keep exploring, and we'll see you in the next video.